Hello students, welcome back. We completed section 2, but we left out a couple of theorems. And at this moment, I did not make up my mind whether to divert those into homework problem set or just cover those. So I'm preparing this video. If I decide is to put those as homework problem set, then of course I'm not going to release this video and use this video as a kind of, review session maybe to explain some homework problems, or maybe I'll include as the normal class session and then do those. In any case, let's begin. This is what we are talking about. Let V be a vector space generated by V1, V2 all the way to Vn, and W be a vector space such that these V1 to Vn are in W. So W includes the generators. Then entire V is a subspace of W, and we have to prove it. So what do we have to prove? So we must prove that capital V is subset of capital W that is every element V, every element of V is a member of W, isn't it? Excuse me, I'm talking and typing at the same time. I'm not really that good at it. So let me read it again. We must prove that W includes V, that is, every element of capital V is an element of W. Now, how do you prove that? Every element, so set arbitrary element, and then let's prove that choose an arbitrary element, small v of capital V, and let us prove that this arbitrary element belongs to W. That's the setup. Are you with me here? We must prove that V is included in capital W, which means every element of V must be in W. So how do you prove that? Just choose an arbitrary element, vector V from capital W, from capital V, and then prove that this small v belongs to capital W. That's the setup. Does everybody agree? Or, well, of course, everybody agrees. It is true. It just that does everybody understand. Let's go back and do this again. So we must prove that V is included in capital W, which means every element of V is an element of W. So how do you set it up? Choose an arbitrary element, and then let's work from here with this arbitrary element. All right? So here we go. Let's choose arbitrary element. V can be written as a linear combination of this V1 through Vn because this generates capital V. So is everybody following here? We just used generating. Okay, and then let's see. W is a vector space, isn't it? So V1 is excuse me, I keep typing the wrong key. So V1 belongs to W, as we said over here. Therefore, X1 belongs to X1 V1 belongs to W. This is what we get, right? So this one belongs to W. All right, and then what do we have? V2 belongs to W. Let's see. V2 belongs to W. Therefore, X2, V2 belongs to W as well. Again, that's because this is scalar multiplication, and vector space close under scalar multiplication. And we'll just repeat this. And then please observe that Vn belong to W. Therefore, Xn Vn belong to W. And then let's go back to this linear combination here. That belongs to W, and this one belongs to W, and then repeat. That too belongs to W. What do we have? This linear combination is actually a sum of vectors in W. And therefore, this whole thing is in W because W is a vector space closed under addition. If you want, I'll be more established. No, I didn't really bother establishing all those. I just skipped a lot of steps. Well, I still skipped a lot of steps here. But anyway, there's a sketch. How about the next one here? Let V be a vector space and let V1, V2, all the way Vn belong to capital V. And the set of all linear combinations V1, V2, okay, form a subspace. Alright, we'll just define that set like this. X1 V1 plus X2 V2 where each X1, X2, and all those are real numbers. So let's find a set like this. This is a set builder notation, and then it consists of elements of this form. X1 V1 plus X2 V2 all the way up to Xn Vn, and then here's condition. X1, X2 all the way up to Xn are real numbers. So this is a set that consists of the linear combinations. Okay, then this is a subspace. Okay, alright. Let's see. Okay, alright. And then what do we have to prove? This is a subspace. So how do you prove that? And we have to prove three things. Number one, 0 is in there. So oops, wrong key. 0 vector can be written as 0 v1 plus dot 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 0 vn. It can be written as a linear combination like this, right? Therefore, it should be element of this set. So include 0, that was easy. Usually that's the easiest one, and usually that's something you should start. Next, close under addition. Okay, let's see. So we have, let's see, I'm kind of running out of character. Let's see. VW, okay. Let's say U is this. W is a linear combination given like this. Y1, V1, Y2, V2, and then all this yn, vn, yes. Both are linear combinations, so clearly they belong to this set. Then what do you get? U plus W is equal to, let's see, parenthesis open, this plus that. But then again, this can be rewritten as x1 plus y1 v1 plus dot 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 xn plus yn. Well, I skipped the second coordinate, but I hope everybody can understand this. So it's a linear combination, isn't it? Therefore, this thing is a member of the set that consists of all those linear combinations. Let's write like this. Then let's align. Okay, 0 done, and then this is theta of sun, and then one more. Let's see. Shall I use V? Okay, V is equal to any linear combination like this. Okay, V is a member of this set here, given by this kind of linear combination, and C is a real number. And then the scalar multiplication, C times V, can be written as C times this linear combination. And this can be written as C x1 v1 plus, and then repeat. combination, isn't it? First component, first coefficient times v1, and next coefficient times v2, all the way up to last coefficient plus vn. So this is equivalent to the form of linear combination. So yes, this thing, scalar multiplication, also belongs to the set. Set generated by v1, v2, all the way to vn. So what we have, defined like this, zero isn't there, usually not very important step, but I encourage students to do it anyway. It gives you some idea to start. And then sum is also in the set. You see, we have these two sums, and then algebraically manipulate so that we have coefficient with v1, or the coefficient with vn, kind of like that. Just prove by algebraic manipulation. And finally, select a point from here, and then arbitrary real number, and then set up the scalar multiplication, and then do some algebraic manipulation. What do you see? We have c1 times first coefficient, c2 times c times x2, second coefficient, all the way up to c times xn, the last coefficient put together. So scalar multiplication is also in this set. So that completes it. If you want a little bit more complete proof, it goes kind of like this. Okay, this one is simple. And then that one, yeah, a little bit more lines than I have down here. And then a little bit more line than what I had over there, because this is a little bit more complete concept proof. But essence, we covered. And then, if you want to see a little bit more elegant expression, you have this notebook to study with.